Good afternoon, ladies and gentlemen. This AI driven game 25. I don't know if you brought up my colleagues, Julien, who else?
Now, to kick us off, ladies and gentlemen, I'm walking you through the background of our project. So PM2.5 refers to tiny urban particles that are smaller than 2.5 micrometers. And because these particles are so small, they're able to penetrate deep into the bloodstream, lung, which may in turn cause things like cardiovascular disease and respiratory disease. So our plan is to develop an AI framework for PM2.5 prediction across 30 minute to 60 minute interval data. We also plan to integrate satellite derived AOD and meteorological data. So basically, we want to integrate satellite data with weather data. So the main problem that we noticed is that PM2.5 exposure is linked to chronic illness. So according to a study that was done by environmental research, about 4.3 million premature deaths occur annually due to PM2.5. This is a large number, ladies and gentlemen. So this is just the PM2.5. It's not considering other pollution factors. So this is a great issue that we need to start with. So as well, if you look on the picture on the right, so we have this headline from last week. This is the DMV area where we saw that a purple alert was declared due to high numbers of air pollution. This was due to the Canadian fire. So even though this is just like a once in a while thing, there are some places that we have noticed that actually experience this high number of PM2.5. So the importance of this project is to support early air quality monitoring and public health disease. So our project objectives are to compare machine learning to deep learning models, to evaluate the impact of temporal resolution, and to assess model performance. All right, so the primary research goal is to build a novel framework for future PM2.5 predictions using AI. We also want to improve models accuracy. So what we are expecting to contribute to already existing research is a comprehensive comparison of machine learning and deep learning. And also we have the new geographical research area. So we realized that in the DMV area, not so many studies have been done on PM2.5. So this is something that we want to focus on. And my colleague will speak more on that later. All right. So we also plan to apply multiple feature engineering techniques, including lagging and rolling. So this will help us enhance our features. So we're able to have more accurate models that will be able to predict PM2.5.
Thank you, Jules. So when it came to listening to other studies and researching this project, we came to the conclusion of, geographically speaking, other groups have labeled this and studied this in 25 predictions in other regions of the area, because this is not affecting one area. So we are one of the first when it comes to studying one area. When it comes to pattern learning, we are also noticing a pattern that other studies did not use the same framework or a similar framework that we are using today, which we'll go in later in depth with the great framework. And lastly is the AOD data retrieval. This is with regards to our deep blue regards and in terms of urban data. When it comes to urban data, however, it's a lot more dense, and that means lower quality overall for our BUK project industry. And as you can see here over the dates, we have between 2019 January to 2023 January. Okay, you can see a clear spike behind here.
So I'm walking you through how the project workflow. So the first stage was to collect the data. So our data came from 3 locations: Howard, Fredonia, and Belgium. And this data was from 2019 to 2022. So this was 4 years worth of data. After that, we split the data into 2 days. The first was the 60-minute time interval, and the second was the 30-minute time interval. So after that, we went through our data preprocessing stage. Then we had the first step being the merging of individual data sets. The second step was the data resampling. And then after that, we removed all missing and negative values from our data. And then next, we utilized linear interpolation for our 30-minute data, which came from our 60-minute data. And then after that, we split our data into 80% for testing and 20% for training. So after that, we went to our model training and testing. So for our machine learning models, we went through 3 phases. The first phase was the baseline, where we used our original data sets, our original data. And then phase 2, we utilized things like we utilized feature engineering, where we used lagging and rolling as our feature engineering techniques. And also after that, we went to feature selection, where we utilized mutual information as our feature selection technique, just to refine our data. And then for our testing and evaluation, we utilize the coefficient of determination, which is the R2 score, and also the root mean square error. And then for our deep learning models, we train 5 deep learning models, and after that we train them and test them.
So more to the three phase component. As Bless was mentioned, we have phase one, phase two, phase three. Phase one was our baseline. So when it came to baseline, we made no extra features in the features. So that left us with five overall to the feature. These five overall total features were wind speed, relative humidity, 10.5, AOD, and temperature. So when it came to the temperature, we had very low R2 scores, but that will go into that more that later. When it came to phase two, however, this is what we added on more features to see how we can get a better result. And these better results that we can see on the board, we have addition of slightly more than 24 hours, 6 to 72 hours. Now, these are all mentioned as average. When it came to rolling, however, we introduced mean and standard deviation to help smooth it out and give us better results. And this led us to 80 people. When it came to phase three, we introduced visual information, and we specifically used visual selection. And with this visual selection, we first categorized the top 40, and we then utilized the top 40 with the highest visual information scores to better improve and refine our process.
Um, Anyway, so as you go further into our project, what we see is the variables the machine was working with, right? We decided to graph these variables in order to give us more context on what we're looking at, right? So obviously we're trying to use these features in order to predict our target with things to five, right? By plotting this, we see that some of our features have relationships with themselves, right? Like you see right here, as relative humidity goes down, we see an increase in our temperature, right? We also see as our wind speed increases, there's a slight increase in our AOD, right? So these are some of the metrics in our features, right? But most importantly, I like to point you to the PM 2.5, right? On average, we see we got a PM 2.5 of 7.5, right? So you go back to last week, the PM 2.5 was 200. That is a significant increase in what we live under today, right? And like my colleague mentioned, there are people who live under 200 PM 2.5 levels every day, right? And it gives us more meaning into why our project is actually important. You know? Now, we tested nine for the machine learning part. We tested 9 models, and these 9 models break into 3 categories. We got linear models, tree-based models, ensemble models. We basically just the ensemble models are the linear and tree-based models, but with multiple techniques inside one model. Here. Now, the accuracy metric that we used was R2. Now, R2 is not an accuracy score. R2 explains the amount of explained variance from our actual values and our predicted values, right? That's kind of hard intuitively to understand. So we decided to graph it, right? Right here, we have a predicted value versus the actual value graph, right? On our x-axis, we have the actual PM 2.5 values. On our y-axis, we have the value that our model predicted, right? So what we want is we want 1-to-1 coordinates, right? So let's say we have a coordinate got 10, 10, right? That means when the actual value was 10, our model would be 10. That's good, right? We're something like 10, 5, that means the actual value was 10, our model would be 5. We do not want that, right? So you see right here on this blue line, the blue line is the best line fit for our models, for our graph, right? So as our R2 score increases, our model performs better. You see this blue line should fit more to a 45-degree angle, like that there, right there, right? The closer that line is to a 45-degree angle, the better our models are performing. Let me go here. Continue. Now, this same graph we model on our top 3 model performance for each category, right? Now, on the right side, what you have is the phase one of our models, right? On the left side, you have phase 3, right? When we implemented our feature engineering, our feature selection, right? So you see on phase 1, before we did anything, just give you the baseline data, our models was not performing good, right? But as you go to phase 3, you see that the best fit line for our points, it increases and it goes more to a 45-degree angle. That shows you from phase 1 to phase 3 that our models are performing better. We go, that's just for the 60 minutes, right here is for the 30 minutes. And see for the 30-minute interval data, this trend also stays consistent as well. Mhm.
Okay, we mentioned RMSE before, but what does it mean? It means root mean square error. So as we can see here on our right, we have our 60-minute intervals in terms of RMSE. On our left, we have our RMSE when it comes to 30-minute intervals. And I want you to pay attention to our Beltsville vinyl on our 60 minutes. As we can see, it is incredibly low. That's very good. However, I want to also bring up to attention that for 30 minutes on those all three stations, each start down still by 60 minutes. This will bring into our conclusion later.
Now, for our deep learning models, we still use the same performance metric from R2 and RMSE, right? But we train them over epoch. So we wanted a different way to visualize our model performance, right? So I say RMSE is the margin of error, right? So the higher the RMSE is, the higher the margin of error is, the lower, the better, right? So if you see here, from epoch 1 to epoch 50, you see our margin of error decrease at each epoch. This shows us that our model is actually learning, right? The R2 score, remember the amount of explained variance, as the epochs increase, our R2 score is going up. So this constantly shows us that our models are improving throughout every phase of learning.
Now we move on to our most important insights. So thing that we found out that was the most important was that multiple data engineering techniques consistently improve model accuracy. And we saw this through our R2 scores. So if you look at the graph, so we have three stations, our pavilion and Belgium. So we look at the baseline phase, which was the first phase, where we only used our original data set. We had that score right there. Then after that, when we moved to our second phase, where we utilize where we use feature engineering, where we employed feature engineering techniques such as lagging and rolling, we saw a significant improvement because our R2 increased. Then in the third phase, where we had our feature selection, we also saw another increase in the R2. So this was the most important insight, showing us the steady increase at every stage where we improve certain things.
And piggybacking off of the last, as we can see here, with our graph on the right is our phase one versus phase three, and we can see the clear difference in quality. But I would also like to bring in the mention that 30 minutes more than those overall throughout the entire testing. And we can see a performance comparison on our one, we can see that there's more than a 10 to 20% gap in the difference between 60 minutes and 30 minutes. Which really does that. And moving forward, in terms of testing being qualified in the situation that we should measure it at 30 minutes.
Now, another good analysis that we found was that our ML models consistently outperform our deep learning models, right? And you see right here from the 60-minute intervals phase to the 30-minute interval phase, you see that our ML models are in blue are always having higher performance metrics than our deep learning models. And I think that's a very good thing. We'll get into why that's important later on. Now, when we looked at our other studies, we have some similarities and differences from our findings, right? Well, we saw that just like other studies, our machine learning models perform better, right? That was considered a lot of other studies, right? Another thing we found similarly that our CAP, which is hyperborean boosting, was the best model that was performed for our area and for other areas as well, right? Now, one difference was that although most studies agreed with us, some studies saw that the deep learning models were outperforming traditional machine learning models, specifically LSTM or long short-term memory models, right? Yeah, so this is a demo video that we did recently that shows you the way our models work.
Good afternoon, ladies and gentlemen. Today I will be demonstrating our live demo that recently affected us Friday the 17th of July. So quickly, I will be running through the three phases that we've already discussed earlier with our original 2019 to 22 data. So we'll be going over this data. As we can see, it's very low. Which reasons are we use hourly and 30 minutes for our Howard, Belleville, and Bedonia. However, for this data set, since it's only from 11:55 to 12:15, I decided to and elected to use 5-second intervals as a frequency. And as we can see from down low, we are receiving very low scores except for cat use, which consistently scored high. With our moving into phase two, however, we can see a noticeable increase in our R2 score and a decrease in our MSE score, like always. However, when it comes to linear I suspect it may be off its limits because of how low it was and then suddenly shooting up to 1 So moving on to cat boost, we can quickly see 61% as well. So taking it from our 23 features to our top 11, we will see how that affects us. And as we've already demonstrated earlier, that it does not drastically affect our score. And if anything, it only refines it and makes it quicker in terms of processing power. So moving on, we still have our same R2 score for linear, cat boost, and random force regression. As we see, they've only gone slightly higher. They haven't dramatically shot up or they have dramatically shot down. Thank you for your time.
So I want to make mention that while we experienced some good results, just like any other research, we experienced some significant challenges. Some of those challenges were synchronizing AOE and terrestrial data. So for when we got our satellite data, we had different timestamps from the weather data. And the first thing that we had to do was to synchronize these times so we could actually use the data. Then another thing is the data preprocessing complexity. We had to do certain steps over and over again until we got the same data at the same time, like I've said before. So some of the solutions that we utilized were temporal synchronization, where we made sure that our times were the same. And also we used linear interpolation for 30-minute data, which came from the 60-minute data. And also we cleaned the data and utilized feature engineering, where we refine our data set more. And then some of the lessons that we learned through this process was that critical preprocessing and synchronization improved prediction performance, which are things that we actually saw while we were doing this, constantly improving and changing certain things when something works.
So some limitations when it came to the project. So first of all, we only have 3 sites. I've already had with those skills. However, that does not cover the entire of the world. Don't just cover the entire of the United States. We couldn't use these numbers or this data to predict about other areas that these stations is not something not covered. In the time range 2019 to 2026, we are currently in 2026. This data is very outdated, and the shoot does not complement our current times, much like and the use of interpolation. So while we did use it for 60 minutes, when it came to the 30-minute intervals, we did use interpolation on our 60 minutes instead of the original broad data that we had and tracking 60. So we simply got our 60 and then we took it from a 60 into our 30. So that could give us a incorrect value, but I would still argue that it would give us still high result. And as I've mentioned before, in general and bias, this is more of a three station limit. You could not go any further than that. You could not get these info predictions as accurate as we have if we Washington. And you wouldn't really get it in Texas or in the So when it comes to privacy and security, we're all safe, don't worry. As these stations are not monitoring your hours for your address or your personal data. These are monitoring on your satellite data and from station data as well. So you are very much safe.
So some key conclusions that we found out through our research was that feature engineering and feature selection were one of the major factors when it comes to improving model performance, right? This shows that the other research that comes to P5 predictions, that these techniques should be used when it comes to trying to give accurate predictions, right? Another conclusion came to that our machine learning models are better in P5 predictions, right? So that means again, when it comes to more research that follows this topic, that especially in the Baltimore, Washington area, that PM 2.5 should be that PM prediction should have a standard of machine learning models. That should be used to predict the concentration. In the future, we want to pick up a few things, right? So we want to improve data by reducing temporal gaps, right? So although we did hourly gaps and 30-minute gaps, right? We do not have nighttime data because AOD isn't measured nighttime. We need sunlight or level of sunlight that isn't present during nighttime to measure AOD, right? So we don't have that. We don't have that type of data. We also want to use additional variables, right? Although we use a lot of variables, there's things like PBL layers or even wind direction that could be used to help predict PM profiles. We haven't used them. We want to explore how those can help our models better predict PM profile concentration. And also, we use deep learning machine learning models. However, we do not use no transformer-based models. And we would like to see how that may affect, how they may perform under the Washington area environment.
Okay, so finally, acknowledgements, I would like to acknowledge our field position, as our woman, the next up is Dr. Lee, Dr. Rocker, and then John Mario, John Bond, the project, we could not ask for that. So, seniors as a family and MSU as a host, Dr. Matt, the director of the senior, sorry, and I coordinators, Elijah and Michael.
We have about 4 minutes for questions from the audience.
Oh. Yeah, so when we first got introduced to the project, we had no background of machine learning, right? So the machine learning models that we used, they were more easier to understand first, right? So we wanted to get a baseline of what we were doing first. So we started with the machine learning models first, right? And as we went into deep learning, we didn't want to put ourselves thin, right? We just focused on the deep learning architectures, right? And before we got into the transformer models. But we had more time, we would have got the transformer models, but just for better understanding, we didn't have much time. Good question.
If there's no other questions, I can ask you a question. And that picture, you guys can take, who belongs to that picture? Not one person that's missing. That's not supposed to be.
It's you.
You weren't supposed to. This is.
Good. So I noticed that at some point during the presentation there was the line on the system graph. They talked about how the line is closer to the number one. This one looks like it's from 5 behind. I don't know if that goes that position.
Yeah. So remember, it's an actual value versus the predicted value on the graph, right? So you go up again. So you see on here. So we want 1-to-1 coordinate points, right? So when it's 10 is 10, right? So as the model, as these points are being plotted, right? The points are going to obviously literally increase, right? So as the literally increase, now we're looking at the best fit line for our point that are graphed, right? So as they're linearly increasing, right, you will see a 45-degree angle because as points linearly increase correctly, you will have a linear increase in our angle, right? That'll be the best one fit. That's why we want a model, a line that's best fit to a 45-degree angle instead of like a 30, as you see.
Follow up on that question. Do you have a nominal value for like the improvement over?
Yeah, for our performance metrics.
Yeah,
we use R2 score. You see how R2 is 0.5. So R2, so it's not an accuracy score, but it measures the amount of explained variance, right? So what variance is basically the spread of data across our mean, right? So basically, as our models predict something, if that variance is small, that's good, right? So we don't want too much variance. We don't want our predicted values and the actual values to stray too far off, right? So the amount of explained variance is good, right? So if it has a low amount of explained variance, that's bad. So that's one that makes it. We also use RMSE, which is like a margin of error.
yeah, but the question was like based on like the three, because I know you said like the line got closer to the 45 1-to-1 ratio. What was like the rate of improvement? Out of like the three test groups, yeah.
Oh, okay. So yes. So from you go to right here. So the rate of improvement is different from each stage, right? From stage 1 to stage 2, we've seen usually an increase of about 0.3, right? Like so from 50 you go to like an 80, right? And from phase 2 to phase 2, you want to see like an improvement like 0.1, right? So from phase 1 to phase 3, we're kind of seeing a 0.4 improvement throughout our data in our 2 score at least.
Thank you so much.